Hi everyone. Today I will be introducing to you some further rules for calculating probabilities. These rules build on the rules that were given last week, so I will begin with some review. Finally, the final rule which we will see today, the law of total probability, is an essential stepping stone towards understanding what's been called Bayes' theorem. And Bayes' theorem is the focus of the next lecture on Wednesday. So let us begin with some review of the rules we have already seen. So the most basic idea of probability is that the probability of any proposition. So for any sentence phi, the probability has to be between 0 and 1. So the probability of some sentence phi might be 0 and it might be 1, but those are two extremes, and all probability lies between those extremes. Now, understanding that 0 and 1 are two extremes of probability leads us to the next group of rules, which we saw already. These rules have to do with how we can understand the probability of logical truths or logical falsehoods. That is, what is the probability of tautologies or contradictions? Now, what the first of these rules says is that any logical truth or any tautology always has the most high probability. That is, for any sentence which is a logical truth, its probability is 1. It's at the top of the possible probabilities. Now, the second of these rules says that if any sentence is a logical falsehood, that means any sentence which is a contradiction, that must have the lowest probability, which is the probability 0. So these two extremes, so any logical truth has to be on the top of the possible probabilities, any logical falsehood has to be on the bottom of the probabilities. Now note though that these say that, for instance, any tautology has probability 1, but that doesn't mean that any sentence with probability 1 has to be a logical truth or a tautology. And similarly, the second rule says that any contradiction or logical falsehood has to have probability 0, but it does not say that whenever there is a sentence with probability 0, it is therefore a logical falsehood. Moving on, another idea is that of how we can know the relative probability of two logically equivalent sentences. And what we know, or what we assume for understanding probabilities, is that whenever you have two sentences which are logically equivalent, which any two sentences which, for instance, if you built a joint truth table, if they had the same truth or falsity under every row, on every row under their main connective, which is to say that they entail each other or that they're logically equivalent, any two logically equivalent sentences have to have the same probability. Okay, so that is this third idea here. Now, in addition to these basic background ideas for how to treat logical truth or falsehood as the two extremes of possible probabilities, and how to treat logically equivalent sentences, we also gave last week two simple rules for calculating disjunctions and conjunctions, the probability of them. And these rules are simple because they are easy to calculate, but they only apply to special cases. So with the simple addition rule, this tells us how to calculate the probability of a disjunction phi or psi. And to do that, we just add up the probabilities of the disjuncts. However, what is crucial to understand is that this simple addition rule can only be applied to a disjunction if the disjuncts are mutually exclusive. That is to say that in the terminology from the previous unit, the disjuncts are inconsistent. They cannot be true together as a matter of logic. So when you have a disjunction where you know that the disjuncts are mutually exclusive, then you can simply add up their probabilities to get the probability of the disjunction. Now, for simple multiplication, this tells us a simple way of calculating the probability of a conjunction. And what it says is that in certain cases, you can calculate the probability of a conjunction by just simply multiplying the probabilities of the conjuncts. But crucially, as with above, this simple rule, can only be applied to certain special cases of conjunctions. And that case is when the conjuncts phi and psi are independent. So if you have a conjunction where the conjuncts are independent, then and only then can you calculate the probability of the entire conjunction by simply multiplying the probabilities of the conjuncts. So one question you might ask is, what is independence? And this is a notion which, since the first day of this unit, we have discussed. And so now, and also since the previous lecture where we introduced conditional probability, we can now give a precise characterization of independence. But first, what is conditional probability? So when a certain condition is fulfilled, when the probability of a sentence psi is greater than 0, you can talk about the conditional probability of some other sentence upon that sentence psi. So if you're asking about the probability of phi given psi, or the conditional probability of phi on psi, what that is given is as a simple ratio of the unconditional probabilities of, on the top, the probability of the conjunction of phi and psi over the probability of psi. So that is the characterization of conditional probability. When you might ask, what is the probability of a proposition given another one? And now that we have this idea of conditional probability, we can characterize the notion of independence and in a formal way. And what it means for a sentence phi to be independent of a sentence psi just is that the conditional probability of phi on psi equals the unconditional probability of phi. That is to say, and the way to understand this in a more intuitive way is that conditioning on psi or given psi does not increase the likelihood of phi. So phi is just as likely whether or not you assume that psi is true. And that's what it means to say that phi is independent of psi. That is, phi's likelihood is not influenced by psi, which is to say that if you condition on psi, the probability of phi given psi is the exact same as the unconditional probability of phi. And now something to note, and which I won't bother proving, but in any detail, but what you can note is that if a sentence phi is independent of psi, then the vice versa holds. That is, psi is also independent of phi. So two sentences being independent of each other is symmetric. So if phi is independent of psi, then psi is also independent of phi. So two sentences, if one sentence is independent of the other, then that other one is also independent of the first. Okay, so this has been some review of the notions which we introduced last week. Now in this lecture, we will go a bit further in building on these notions. So here are a few more rules which are important to keep in mind. First, there is the negation rule, and the negation rule tells us how to calculate the probability of a negated sentence if we know already the probability of the unnegated one. So what this says is that the probability of not phi equals 1 minus the probability of phi. So for instance, if the probability of the coin landing heads is 1/2, then the probability of the coin not landing heads, i.e. landing tails, is 1 minus 1/2, which is also a half. Or if, for instance, we had an unfair coin that landed heads 3/4 of the time, the probability of heads would be 3/4, which would mean therefore that the probability of not heads, i.e. tails, would be 1 minus 3/4, which is 1/4. Now we can also flip the negation rule around, and if we happen to know the probability of not phi, then we can calculate the probability of phi by simply subtracting from 1 the probability of not phi. So hopefully you can see how from the negation rule you can derive the flip side simply by doing some algebraic tricks by adding the probability of phi to both sides and then subtracting the probability of not phi from both sides. And that's how you see that these two rules are just two sides of the same coin, so to speak. Now, the third one is the idea of logical entailment. So just like above, where we said that two logically equivalent sentences have the exact same probability, if we have two sentences which are not necessarily logically equivalent, but rather if we have two sentences where one, phi, let's say, logically entails the other. So psi might not logically entail phi, but we do know that phi logically entails psi. And if that is so, then we know that the probability of psi, the one entailed, cannot be less than the probability of the one that entails it. So imagine that I am flipping a fair coin a bunch of times in a row. In this case, the proposition that the coin lands heads twice in a row for the first two throws logically entails a proposition that it lands heads the first time, regardless of what happens after. So in this case, that the coin lands heads twice is phi, and that logically entails that the coin lands heads the first time, which is psi. And accordingly, in accordance with this rule, the proposition that the coin will land heads first, it has a probability which is much higher than the probability of the proposition landing heads twice. So in this case, because it's a fair coin with independent throws, the probability of it landing heads the first time is 1/2, and the probability of it landing heads twice is 1/4. So here we have the probability of the entailed proposition as higher than the probability of the proposition entailed. And intuitively, the reason this is because the claim that the coin will land heads first is a weaker claim than the claim that the coin will land heads the first and the second time. That is to say that phi in this case, that the coin lands heads twice, is kind of a conjunction of the claim psi that it lands heads first and the claim that it lands heads second. So phi in this case says something logically stronger than psi. Phi says that it'll land heads first and second, whereas psi simply says that the coin will land heads first, and it doesn't say anything about what will happen after that. So because psi is claiming something weaker, it's entailed by psi. Psi is claiming something logically weaker than phi because it's entailed by phi, but it does not entail phi. Because it says something logically weaker, it is easier to be true. It's more likely to be true. In this case, the probability is 1/2 versus the probability of landing heads twice in a row being 1/4. Now, at the very beginning of this class, we talked a bit about how there are certain cognitive illusions. That is, we looked at visual illusions where our perceptual system delivered us something incorrect about the way the world looked. And we saw that these illusions persist, despite that we're being told how these illusions work. So for instance, if you look at the very first reading again, there's an example of a visual illusion where there's a bunch of dots or circles on a background, and this scene looks like it's moving or there's certain waves moving through it, but in fact it's not moving at all. And the reason your visual system provides that illusion is that it has certain hardwired ways of detecting how your environment looks. But those hardwired ways, because they're so fast and automatic, make certain mistakes sometimes. And by analogy with the visual illusions and how our visual system makes certain mistakes sometimes by employing really fast automatic rules, With an analogy with that, we can think about cognitive illusions, which are errors or systematic errors in the way we reason based on us deploying certain heuristics or quick tools to answer the question. Now that we understand how this rule of logical entailment works, which is that if a sentence phi logically entails another one, then the probability of phi could not be greater than the probability of the one it entails. If we understand rationally at a general level why this holds, we are now in a position to see a corresponding cognitive illusion. And this is a very famous example. So I want you to consider the following setup. And this is about someone named Linda. So here's what we know about Linda. Linda is 31 years old, single, outspoken, and smart. She was a philosophy major in college. When she was a student, she was an ardent supporter of Native American rights, and she picketed a department store that had no facilities for nursing mothers. So this is all we know about Linda. Now, let me ask you the following question about probabilities. Which of the following statements is more likely? 1, Linda now is a bank teller, and 2, Linda is a feminist bank teller. So if we were to translate this into our formal language, 1 would just be simply the sentence B, which stands for Linda is a bank teller, and 2 would be the sentence FNB, which is that Linda is a feminist and a bank teller. So given this setup about what we know about Linda and what she did when she was in college, is it more likely that she's a bank teller or that she's a feminist bank teller? So take a moment to answer that question for yourself. Now, many people answer this question by saying that actually, too, FNB is more likely or has a higher probability than B. However, that is a fallacy. It's a kind of illusion because it seems very intuitive that 2, given this setup, is more likely because here we know a bunch of information that leads us to think that Linda is a feminist. So we naturally think that this sentence, including the claim that she's a feminist, will be more likely than simply that she's a bank teller, which seems unrelated to everything we know about Linda and her past. However, we saw above that when you have a sentence phi logically entailing another one, then that sentence's probability cannot be higher than the one it entails. And we also know from deductive logic that a conjunction, which has one of its conjuncts as B, will entail that conjunct B. So F and B entails B because a conjunction cannot be true unless both conjuncts are true. So that means that F and B entails B, that is, the claim that Linda is a feminist bank teller logically entails that she is a bank teller. And therefore, according to our rule for the probability of sentences which logically entail one another, that means that according to the rule which says that when you have a sentence which logically entails another, that first sentence's probability could not be higher than the one it entails. We therefore know that the probability of the conjunction cannot be higher than the probability of the conjunct. So that is to say that given the rules of probability, it is actually the case that 2 cannot be more likely than 1. However, many people find it intuitive that 2 is in fact more likely than 1, and that's because you might think you focus too much on the feminist part and you don't realize that 2 is actually saying something logically stronger than 1. It's saying 2 is saying, in addition to Linda being a bank teller, she's also a feminist. But in this case, because you're saying something logically stronger than simply that she's a bank teller, that cannot actually have a higher probability because 2 includes a claim that Linda is a bank teller. So if the probability of her being a bank teller is low, the probability of her being a feminist bank teller will also be low, regardless of the additional thing. Okay, now moving on. Here is, to conclude this first video of this lecture, here is a rule for calculating the probability of conjunctions even when the conjuncts are not independent. That is to say, to review again, the rule which I gave you last week for calculating conjunctions only applies when the conjuncts are independent. That is to say that the likelihood of one does not depend on the other in any way. But we can also calculate the probability of conjunctions even when they're not independent. Okay, so what we do is, instead of just simply multiplying the probability of each conjunct, what we have to do is multiply the probability of one conjunct conditional on the other by the other's unconditional probability. So for any two sentences, the probability of phi and psi equals the probability of phi given psi times the probability of psi. And one thing to note is that this rule, again, this rule helps us calculate the probability of conjunctions regardless of whether the conjuncts are independent. So even if the conjuncts are independent, you can still apply this rule, and it'll actually end up being the exact same as this rule here, because what it means for phi to be independent of psi is that phi's conditional probability on psi is the same as its unconditional probability. So the probability of phi given psi can just be replaced by the probability of phi when phi and psi are independent. And before moving on to the next video of this lecture, where I'll give two more very important rules, I'll just note that I discussed this rule here in greater detail in the previous lecture on conditional probability. And I also, in that video lecture, discussed how to apply this rule to problems involving what are called Laplace's urns, or certain problems involving urns. And I discussed in detail how to solve those problems, and these will come up on the readings and quizzes or the problem set for this week. Okay, so please review the last lecture for more detail on this rule and how to apply it